So I'm Vivek Kashyap, and my colleague Ping, he is in Beijing, so we'll be co-presenting this. I'll cover the first half, and Ping will cover the latter. Ping will talk about congestion and reinforcement learning, the work that he's investigating there. And I'll take you through some of the aspects of congestion management that we are interested in, and then a simple proposal. So probably I should take about 20 minutes, and then Ping can take on the take you through to the end. So as we have been discussing over the last couple of days, there have been multiple talks on congestion. This is yet another, but with a slightly different focus. If we look at the data center from a very high-level perspective, you can consider it 2 primary networks, or depending on how you want to count, 3. But the basic idea is that there's a front-end network, which is more akin to a cloud network, because it is customer-facing. It takes the inputs for all the requirements, may run various workloads, various VMs. And then there's the backend network, where we may have our training and inference clusters. There's also storage, which may be on the same RDMA network. So you need the high performance, high bandwidth, and low latency network for this traffic. And what is this traffic? Basically, as most of you probably are already aware, and we have talked about in the last couple of days, the high-speed, low-latency requirement for AI, ML, or HPC traffic is the basic driving force here. AI, ML traffic is systolic, it's periodic. As we go through the gradients as they are calculated across the epochs. It is bursty, large messages, and of course, latency sensitive. You do not want too much variance in your tail latencies, because you want all the work to complete in a reasonable time, and the variance causes you trouble or throws you off. The same is the case with HPC, except that you may not have as large messages, you have smaller messages, but it's latency sensitive as well. Into the mix, the other RDMA traffic is the storage traffic, which may not have similar requirements, but it needs to be fast enough to provide the input to the other workload. And the protocol of choice here, of course, is RDMA, because we want that high performance and get the CPU and OS out of the way. So essentially, the challenge is to ensure low tail latencies and high utilization. We do not want any network delays, because that wastes time, takes away, adds to the cost, because you're blocking your expensive GPUs from doing their work. And what that means is that you need to manage your network. You need to have good congestion control. Last point here is that the technology of choice for all this is Ethernet, because one thing is that it is capable of providing this kind of performance, the high speeds going up to 400, 800 gig nowadays. And it is omnipresent, it is cheap, it's open, so everyone has it. And the only con, one may say, is that it's a lossy medium. It does not assure packet delivery, and so your ULPs have to ensure that, or you have to work that into your solution. It's not like InfiniBand. So with that background, let's take a look at some of the aspects as to why there is so much churn in the industry with respect to RDMA. We have had talks in the last Netdev, as well as earlier on here with on Ultra Ethernet and Google Falcon, which are all essentially the result of finding a ROCKY deficient. A few of the problems which I'll just mention here is that ROCKY standard, as it was the default standard, does not have a good, or it follows the go back n semantics on loss, which means that all the packets that were transmitted since the last successful ACK have to be retransmitted again if there's a loss. And that is, of course, very inefficient. It uses PFC, which has its own set of problems. I'll just mention a few, and we can discuss if someone is interested. But it can cause spreading of congestion or blockage all the way into the network when you have head-of-line blocking at one place. In the worst case, it may even cause deadlocks. To get around this, DCQCN is used, which allows for much larger networks and for much more efficient deployment by the use of ECN, where the switches mark their packets if their queues are above a certain threshold, and the receiver can send back the packet to the sender to recalculate the rate, to recalculate their send rate and manage the congestion. The negative here is that DCQCN is has to be well tuned. It has multiple parameters, and if something changes in the network, you got to retune again. The other aspect is in terms of burstiness. It may have often PFC is still used as a backstop, because in burstiness it may end up dropping quite a few packets. So with all this in the mix, and the desire for high utilization and low latencies, there have been multiple new investigations, multiple new methods and proposals from various companies and standards bodies, often leveraging the research done in TCP for congestion. So I'll just name a few. For example, Intel's Gaudi or NVIDIA's Resilient ROCKY have introduced certain mechanisms such as SAC or out-of-order packet acceptance or multipathing, etc., to overcome these limitations. There are other proposals from Amazon. For example, Amazon implements SRD. Alibaba has HPCC. I mentioned Google Falcon earlier. Tesla has proposed TTPoE. And of course, the standard Ultra Ethernet being proposed in Ultra Ethernet Consortium, which hopes to overcome all these limitations. And all these limitations, of course, are, like I said, on how to manage your traffic to avoid congestion. There are multiple signals for congestion that are utilized, such as from the network as well as from the switch. Sometimes the protocols may use only the network signals, and some other congestion protocols utilize the switch signals and a combination as well. To name a few, or to give an example, the loss-based protocols are such as TCP Cubic, TCP Reno, which have been very successful in the internet, but they are not that useful in the data center. The notification-based one, like with the ECN notification, I mentioned DCQCN. Similarly, there's DCTCP, which also looks to the ECN feedback from the switch when the queues are getting filled to a certain threshold. The difference being that in DCTCP, the feedback is sent in ACKs, whereas in DCQCN, a special congestion notification packet is sent back, which on a different class of service or different traffic class to let the sender then recalculate their sending rate. There are delay-based signals, such as used by Swift or TCP Vegas. Now, an interesting aspect between the two signals that I mentioned, ECN, which is, of course, coming from the switch, is a leading indicator of congestion. And that's because when the packet leaves the switch, it is essentially giving the information of the state at the given time, because the queue is being filled by packets after that, but once the threshold is reached, the threshold that is marked for the ECN transmission, that's when the packet's going out and it's carrying the ECN bit. So when the marking is done, you are essentially stating that possibly congestion is going to develop or the switch buffers are getting filled. The same packet, were it to be used for RTT or delay calculations, would have no such indication, because at the time that it's going through, there is really no congestion in the network. The packet goes through, and the feedback in the ACK that goes back to the sender is giving the picture for that packet, whereas there was actually the queues in the switch were getting filled up. So it's a lagging indicator. But at the same time, the delay calculation gives you a very precise information. It is a multi-bit information, so you get a lot of, you can be very precise, and the delay protocols have been very successful. One other aspect where switch may be used is with in-network telemetry, which is what Alibaba's HPCC does. It gathers the network hop by hop information from the switches, telling about the queue lengths or how many bytes have been transmitted and the capacity, etc. So HPCC is able to provide fairness and load balance at the different flows quite well. I should also mention one of the interesting protocols here or innovations here, which is that, as I mentioned, the ECN is, the marking is done at the time of the egress, and the response goes back when it reaches the switch, the receiver, and then back to the sender. So the time is still the RTT-based time in which you get your feedback. But what if you were to get it even faster? And that's where the Bolt protocol comes in, where on the ingress, the switch is modified to actually send back the send feedback back to the sender in sub-RTT times if it sees its queues getting filled up. So as you can see, there are lots and lots of protocols, and I've just mentioned a few, different mechanisms and different signals. And these are not just these signals that are affecting the overall performance or the overall control. There are multiple other factors, whether the overall end-to-end flow is sent over multiple paths to work around possible congestion points or to load balance them better, to have better entropy, whether out-of-order placement is enabled or not, whether you do go back N like we talked about with Rocky, or whether SAC is implemented. So with all these combinations, if there are multiple workloads sharing the same data centers, sharing the same links in some cases, or for some paths, then these flows may not always work together, or the results may not be exactly what we want in terms of whether we are looking for fairness, we are looking for completion time, and whether we are looking for scalability. So one of the aspects to consider is, do we always just isolate different workloads, different flows? For example, we put all our storage Rocky traffic on one set of QoS points and our HPC traffic on another, or AI/ML traffic on another. And that's possible, of course. That requires more work and more cost. So again, just looking at some of the three of the examples, I already talked about the delay-based like Swift, and HVCC, which is int. Now, the SMART protocol looks to combining both the signals into one. It also uses packet trimming. Packet trimming is the case where the router, instead of dropping the packet, will trim the packet to just the headers and send it back to the receiver on a different egress queue or different traffic class, so that the receiver can then react to that and manage its sending of the packets, or determine what its window needs to be. But in that, I would like to point out one example here. I took a snippet of the algorithm that SMART implements. And if you look at the fact that it is indicating, it may receive a packet which says that ECN was marked, but the timestamping on the packet on the ACK gives the information to the receiver that the delay is still below the target delay. So you are still not seeing any congestion. So SMART says that, okay, ECN bit is set, therefore there is a possibility that congestion is going to develop. But at present, it isn't there, so let me just cautiously decrease my send rate, the packets at my window, so that I send less into the network. Supposing this is being shared, the link is being shared with a delay-based protocol. Now, it's getting the same signal, but not the ECN signal. It sees no difference, and it may say that actually, I'm not seeing any delay increasing. It's well within the bound, so maybe I should increase a little bit. So there's just a theoretical point here that two congestion protocols, if they're running on the same network, getting the same signal on those, sharing some path, may react differently. And that's one of the aspects that we are interested in. There is, of course, simulation, and lot of simulations have been done with various models, but the models do not always capture everything. Often we need a practical insight into what is happening on our specific network for our specific set of workloads in our specific setup. And for that, we have a simple proposal. So what we are proposing is that we develop and implement a Soft-RDMA stack, which can take different congestion control algorithms or components as a module, and with a standard set of signals that may be passed to it, so that we can test out in the lab, in the software, without needing the specialized NIC, of course, for doing these experiments, for validating how the different congestion control mechanisms will perform in our network, in our specific data center or cluster, and for functional verification, testing out new things. And I further would say that we could even modularize it so that you can define certain personalities for how the data is sent, what is the packet format for the packet builder mechanisms, since there are multiple of them. There's Rocky, of course. I just now mentioned Ultra Ethernet. There's Falcon, and so many others. So that's the primary proposal I wanted to bring here. Of course, this solution won't be performant, and it's not all that radical. There is Soft Rocky, for example, and what we are talking about here is making it more generalized, making something similar, more general, with the modular congestion control, programmable congestion control module that can be modified on the fly or as needed. Now, performance is certainly not feasible with this, but of course, what you can always look to is that It is certainly doable for the previous generation of solutions. For example, it may be that my links are 100 gig, but I can probably work on a Soft-RDMA solution for my 40 gig networks, or 400 to 100, the N-1 solution. The other aspect is there's a couple of charts that I picked from last Netdev, where it was presented as part of the discussion on Falcon. As you can see, this is Falcon implementation on Intel IPU with the rate update engine, this circle blob here. That is what implements the congestion control. And it's already modularly defined. So certainly on an IPU, you can provide updates or provide the interface to programmatically modify the congestion control and essentially have the same kind of variance that we are looking for, but on an IPU or on in the hardware, and therefore get the performance as well. So that brings me to the end of the first part. I know I spoke in a continuous stream, so I'll stop now for any questions.
So you don't actually need an RDMA stack, right? I mean, to do what you're doing, what you're proposing, you just need a UDP transport. You need a packet transport that has all the signals that you want. There's no RDMA semantics has no impact here.
RDMA semantics doesn't have any impact, but my rest of the endpoints in that network are, say, they are NVMe over Ethernet over RoCE components. So that's the real aspect.
Right. But I'm saying for evaluating congestion control, that operational semantic is not showing up.
Okay, so fair point.
This could just be a simple UDP packet generator that says, send these signals and see what happens. But I think the middle is more interesting because you want a real switch in the path, or you need something that generates some kind of buffer buildup, because otherwise you get nothing. Right? So the ECN and the round trip signaling that you're talking about, and I'm assuming at some point you want to be able to model CSIG and bolt like back to sender type things. So the switch is the more interesting thing, right? The endpoints are the fairly simple. Here's a bunch of bits in a wire.
That's a good point, though I would clarify here that just testing out the congestion control was not the primary driver, though that is a major part of the solution. The reason for discussing with the RDMA aspect is multifaceted. One is, of course, because our rest of the endpoints are running RDMA protocol and we want to participate in that. Congestion is certainly adding to it, but it's not the complete picture, so that we can validate other aspects as well. For example, as I mentioned, there may be certain endpoint-to-endpoint modifications that affect the overall flow. Of course, it's already there, but I'll use it as an example, such as out-of-order placement, etc. So that is one of the reasons to look to creating a somewhat, or suggesting a somewhat more comprehensive proposal, including RDMA. But yeah, if the focus was purely on congestion control, irrespective of what the workload is, what the endpoints are actually using, then yeah, something simpler, focused purely, as you suggest, would be very useful.
That makes sense, but what you're then saying is, like, even on the list that you have, and that list is not exhaustive, you would need an endpoint per, right? You would need an endpoint for RoCE, you'd need an endpoint for Falcon, UEC, SRD, blah, blah, blah. So, because the moment you go into that, it's no longer, RDMA is not standardized enough. The way the RDMA call gets converted into a messaging or a transport protocol means this becomes like a 10x program right there, right?
True. That's why I sort of, let me go back here. it does become more complex, but that's why I called it different personalities. It doesn't mean you implement all of them at the same time. We start with one or two that are of more interest to us. Perhaps we start with Ultra Ethernet. So, any other question? All right, I'll pass it on to my colleague, Ping.
Hello?
Hi, Ping. Yeah, you go ahead and present. You can present on Zoom, and I think it'll be seen by all.
Okay, so let me share.
Perfect.
Okay. Okay, so let's start the next session for the reinforcement of congestion control. So we know that with the large language model get very popular, and much work networking is targeting for the AI. And we might think about another question. So how AI can support, can help networking? So this is some session we know, and we do some testing and POC to see how we use AI to accelerate networking. So we call it as AI for networking. And just now, Vivek said that we have much work in the DC. RDMA is popularly used. And so it means that the main protocol in the data center might use RDMA. But we also saw a very interesting source is interesting thing that much RDMA is enhanced so that it can be TCP. So it means that RDMA need a more reliable transport. So speaking of that, we might also think about could we think about how we do in the original TCP protocol. So we did some academic research for what happened in the TCP congestion control and how the work is ongoing. We found the interesting thing is that before 2020, and much work related with the TCP congestion control is much related with the heuristic algorithm. So there are much work to do. And after BBR is released, and I think the academic has turned to another field is the machine learning, how to use machine learning to accelerate the congestion control. So we'd like to summarize some work they did and provide some thing that Intel can help in this transformation. So speak of the AI in the congestion control, the most used one is the deep learning, deep reinforcement learning. So for the deep DRL, so what is the component? Let me see. The first one is the state. State is that the thing you can observe from the environment. So the state means that it is something you observed. So take a large language model, take a transformer as an example. So we will not do everything. We just pay attention to what we should do. So state is something we observed from the environment. And the reward is the functions. So this is a strategy to support how we want to get the right congestion control. Congestion control is sometimes is very customized, and different people might use to get different algorithm and utilization of the network. So reward is used to give the AI the hint how we want to get the maximized result from the congestion control. So different reward functions might mean that different results it can achieve. And the work is to train a policy that can maximize the reward finally. And the action, what is the action used? Action in the reinforcement side is the result, how the agent do so that the action can be used applied to the state so that the state can be changed. For each of the change, then we can calculate a reward. So then next time, based on reward, we know that this action is good or not. If it's good, so it means that we will continue or strengthen the action. And if not good, so it will maybe come to another way to do that. So the action here is the reinforcement finally achieve the result. What we do in the congestion control side is two parts. One is the congestion window. So this is mostly used. For example, BBR in the TCP side, it will calculate the bandwidth, the BDP, and then it calculates what is the most suitable congestion window, and it will sometimes also can measure the latency and the bandwidth. And sometimes there's another point is to use the sending rate. The sending rate is also can be used so that the sender know what the rate is acceptable by the receiver. So this is a general overview of how congestion control with the help of the reinforcement learning. And we applied and we read much paper from the academic side. And we also do some environment setting to see how it can help in the real networking. Then we found some challenges inside. The first one is that how to balance the heuristic and machine learning. For example, for the heuristic algorithm, it has a clear rule. For example, if I got a packet loss, we will reduce the window, and we will also get some state. For example, we need to get to congestion avoid state. So this is there's clear rule how to do when we got something. So it's a kind of state machine. And but for the machine learning, we don't have that state anyway. And we also need to trial for most of the time to see what is the best. As I mentioned, when we observe the state, we know that we want to do something. But what's the result? We need to try. So there's much work to do for the trial exploration so that we know what is the best result. A training model needs to be running for some time, and then finally we know that in each situation, we will do this. And then it can possibly achieve the best results. And the second challenge for us, we found that, example, currently we are mostly based on Linux kernel, and congestion has there's a congestion framework so that we can leverage. But sometimes, the reinforcement learning, the work mostly is done by user space. So we need to leverage the training and then the inference framework from PyTorch, from TensorFlow. So we could not do that in kernel side. So this means that we have to design an interface so that the congestion control can be performed in the kernel, but the reinforcement can be done in the user space. So what's the best interface we should do? So this is another challenge we need to face. And the third one is we know that reinforcement can help us, but we know that the package is a very quick. We need a very small time, the minimum time we can consume for each package. So if we leverage reinforcement and per packet base, so there's much challenge. I measure the inference rate by a standard TensorFlow by a reinforcement model. So the result is a K level. So we can achieve maybe 1K, 2K per second instance per second. So it is a very slow comparing with the packet pacing. So how we can balance that everything? So this is a general way of that. And to speak of that, to give a clear information example how we can do, we can take example from academic paper. This is Aurora. Aurora, I found that this is the very first and the very early DRL implementation of the congestion control using reinforcement. And as I mentioned that we need to define actions and state kind of things. And it has, for example, the action. The action is that, as I mentioned, we have several options. Sometimes we need to change the congestion window, and sometimes we can change the sending rate. So the Aurora is using the rate limit, the sender rate functions, and the state is that state to define what is the current situation of that. For you can imagine that for each time we can fetch the kernel congestion status, such as the packet loss, the RTT, the throughput, the latency, RTT, the kind of things. And this is one snapshot for current congestion situation. But we could not just rely on this, because even if we have the same situation, we could not know what is the change, what's the difference between the current status and the status 1 second ago or 2 seconds ago. And just like stock price, for example, stock price is always jumping, and we could not do just based on current state the price. We do the judgment. So for the statement, for the state, we are using a different history, then combined together so that it can be one of the status to do something. And the reward is the work we can measure, and then it can be defined by packet loss, throughput kind of things together. And the algorithm is used by PPO algorithm. So from this paper, we can see that this is a very adaptive for based on the reinforcement work. So this is the blue side is the traditional one from cubic, and the IL based is it can best adapt to the changes of the rate. But by deploying this model, I did to reproduce this in our environment, but we found that there's some problem here and how we can address. The first problem, as I said, that the throughput here is a bit small. So how we can adapt to the data centers, the packet rate is very quick. And second is that how to adapt the inference. So each paper we are using use the packet-based inference. But you can imagine that in our data center, it is very difficult to measure the per packet status. So based on that, we do some work to absorb some of the good material practice from the original academic paper, and we also do some performance optimization to how we can provide the best inference. So basically, we found that a practical way to do the reinforcement for the congestion control have two sides. One is that we can do this in for two control. Firstly, because we could not do the full per packet inference, so we have to do that. We let the TCP algorithm based on the normal ARC-based logic. So it has a local congestion control controlled by the heuristic. And secondly, that we can do the second level of the control. The DRL will calculate the congestion window for the session. And then sometimes we also understand that this congestion window might not fit for current situation because it is still need time to training. So in this example, we need to choose from the heuristic and machine learning so that we can do a measurement. In PCC paper, there's a concept named utility. So utility is used to measure which one is the best, the current local one or the IL-based one. And then user-based utilitarian will notify the mechanism is implemented. So the advantage is that we can still use the reinforcement for a high throughput traffic. And on the other hand, we can leverage Intel AMX-based algorithm to optimize it. So in Intel internal, we have a library we based on AMX so that we can provide the a high efficient packet level inference, so that we can achieve a higher inference rate for this. So finally, we can introduce the software architecture here, as I mentioned. In the kernel side, we still use the kernel heuristic congestion algorithm, and then it has two interfaces. One interface is that to go from the kernel to user space. So we are using a netlink based because we have multiple FDs. There are too many FDs, so we need a system for the netlink, so it can be absorbed from the kernel to the user space for a monitor block. So this block will do the observation, go to the DRL agent. Then the DRL agent will measure the current data, and then it will perform an action. And this action will be used for a congestion window. So finally, it can go to the user set stop option, go to the kernel. So this is the thing we are doing. So basically, we want to combine the heuristic and the machine learning, and also we want our work to benefit, for example, device memory, DCP. So this is a hot topic in Netdev. We are also doing the network device memory TCP, and device memory TCP is a data plane based, and for the congestion control side, especially for the sender side, we can leverage this work to help us to improve the total performance. So yeah, basically this is my presentation. Do you have any question?
Yeah, the architecture is interesting here. How far along is it? Have you experimented with how well that works? And for example, if there's kind of interference between the heuristic and the ML-based algorithms and the decisions they make?
Yeah, so for the congestion, the heuristic side, it will still based on the packet level. For example, we are using BBR. This is by default in the TCP kernel, and then it can generate the congestion window. But we need a time. We need to accumulate a batch of the data. Then this data will be submitted to the DRL agent. So this DRL agent will deliver the actions. So you can imagine that the heuristic algorithm is local based, and the DRL agent is global based. So it will based on the overall solutions, the conditions, and then dispatch what should be the right one for this session of the congestion window. Okay, and I think I have 2 minutes, so last question.
Okay.
Hello? Okay, thank you.
If there are no questions, we're done then. Thank you very much.
Thanks, Peng.
Thank you. Thank you. Have a good day.